Okay, I think we are ready to start the morning session. And it's a pleasure to introduce Konstantin Zarembo, the first speaker of today. And he will speak about integrable D-branes and one-point functions. Please.
I'll talk about the work with Charlotte Christensen and Dean Longwu. And it has to do with one-point functions in the presence of D-branes. So if we have a D-brane, then a string, it's just a surface in space-time where the string can end. Basically, it's just boundary conditions imposed on the string. And they can be Dirichlet and Neumann in perpendicular and longitudinal directions. Or they can be D-brane can be magnetized, which simply means that the boundary conditions are mixed, Dirichlet-Neumann. So these boundary conditions, in general, will break integrability of the ambient string. But in some instances, they do not, and these are precisely the cases we are interested in. So if they break integrability, then we basically can do nothing, because scattering on the D-brane, or so that the magnet propagating along the string will not only reflect from the boundary, but it will also create particles, and this will produce a mess, and so we will not be able to solve the model. But if integrability is preserved, the scattering is elastic, and moreover, for integrability to work, it has to be consistent with the bulk scattering. So the reflection of the brane should satisfy certain conditions that are express consistency with the bulk scattering of excitations of the string. So then, in such a situation, we can define a partition function. So now this is a partition function on a half-infinite cylinder. That's the simplest object we can compute in the presence of the boundary. And well, we can take the limit where the cylinder is well, literally half infinite, so very large. And the partition function then will have an exponential factor that scales with the length of the cylinder, and so this will be just the same free energy that characterizes closed string. But then there will be a prefactor that's known as G function, or boundary entropy. And the nice thing about it is that it is calculable, systematically calculable by thermodynamic Bethe ansatz. So it's as calculable as the bulk free energy. So in ADS CFT, well, the string being infinite means that it goes down to the boundary. So what we are considering is a string that ends on the D-brane, or begins on the D-brane, then propagates in ADS, and then it approaches some point on the boundary. So this means that we are studying a correlation function of a single insertion. So it's a condensate. So in the presence of the D-brane, local operators develop condensates, and the condensate is described by this process. So a string emitted from the boundary and then disappearing in nowhere because it can be absorbed by a D-brane. So the D-brane can, so integrable D-branes were actually classified by Decalinos in 2011. And they can have different shapes. So D-brane can go parallel to the boundary. That will describe Coulomb branch, as where the gauge symmetry is Higgs. It can have one leg on the boundary and then go to infinity. So this would correspond to a defect inserted in the boundary. So we'll be dealing with a defect CFT. Or it can have both legs on the boundaries. So this would correspond to insertion of some very heavy operators. And if you're considering a string on top, then this would probe these two operators. So we'll be dealing with a three-point function. But I'll concentrate on the second case where the D-brane describes a defect in conformal field theory. So what does it correspond to in the field theory context? A D-brane is a classical object, so in string theory it's just fixed, it cannot move. Likewise in field theory it is described by some classical field configuration. So if you have an operator, and let's say we are at very weak coupling, at zero coupling, well, to the leading order we can just substitute this classical solution in the operator, and that would give the leading order of the correlation function. So in the spin chain interpretation, this immediately maps the problem to computing an overlap of whatever state characterizes the operator with a new state that isn't used by the D-brane, and which is obtained by simply multiplying the classical fields and taking the trace. So this is the type of objects I'll concentrate on. And there are two basic examples of integrable theory, n equals 4 and ABJM. I'll talk about the latter one. So it's a three-dimensional theory, just reminding you how it looks like, with the Lagrangian that contains two Chern-Simons terms for two types of gauge fields, which come with opposite signs and a common coefficient that has to be quantized. And then on top of that, there is matter in bifundamental representation, which contains both bosons and fermions, and the theory is actually supersymmetric if the coupling constants are adjusted appropriately. And it has a well-defined Hooft expansion, which is the expansion in the inverse of the Chern-Simons level. So the coupling constant is the ratio of number of colors to the level. And it is known to be integrable. So what kind of defects exist in this theory? Well, we will be looking at the domain wall defects, so they are codimension 1. And they better preserve some symmetries. And particularly if you want to preserve supersymmetry, they should have zero energy in some sense, or smallest possible energy with given boundary conditions. And basically solitons that are supersymmetric, they always satisfy equations that are first order, not second order in derivatives. So the action then can be written as a total square plus some boundary terms. It always happens like that. So BPS monopoles, instantons are of this type. And here too one can write this horrible Lagrangian that I showed in the previous slide. It can be written as a total square, but only if we restrict the fields so that originally there were 4 fields because the global symmetry of ABJM is SU4. But if we say that 2 of them are equal to 0, then the Lagrangian or the energy, static energy of the remaining 2 fields can be written as a total square. So one needs to use some identities that are only valid where the group SU4 is broken to SU2. Once the energy is written in this way, we know that the lowest energy configurations should be such that this modulus squared is 0. And these configurations are automatically supersymmetric, like anything supersymmetric in a given sector has 0 energy. So the BPS domain walls are such that they satisfy this condition. So we get the first order equations, nonlinear, so they're cubic cubic equations, and in principle not easy to solve. But nicely, these equations can be written in the form that appeared many times before, and in particular in n equals 4 superangles. So if we write the equations for composite fields, namely for a bilinear of the original scalars, then we can expand them in Pauli matrices. So because the indices alpha and beta run from 1 to 2, and it's natural to decompose them in the basis of Pauli matrices. So then the simple calculation shows that equations for the coefficients are nothing but NUM equations, which are very famous in mathematical physics. In particular, they arise in n equals 4 superangles when we describe the supersymmetric domain walls. So basically, the domain wall in ABJM is mathematically the same as in n equals 4, but you need to find appropriate variables. So the simplest solution is, well, these equations don't have smooth solutions. There should be, they have to have poles in X. And the simplest solution has just a single pole. So the fields simply decay as 1 over X and go to infinity at the position of the domain wall. Then for the coefficients, we get just algebraic equations. And these algebraic equations are simply commutation relations of SU2. So the solutions are characterized by embedding of SU2 in the color group of the original theory. So SU2 has well, many representations. So so the solution will be then characterized by the dimension of this representation, which will be Q minus 1 dimensional. So if one multiplies fields in the opposite order, one can show that, well, again, the same exercise shows that the coefficients are representation matrices of SU2. And this representation will be Q-dimensional. So one can also write an explicit formula for the original Y variables, and this solution was found by Terashima in 2008. And what it describes is a domain wall, so that the fields are, they depend only on one coordinate. So on one side, one should, so the fields go to infinity on the domain wall, on the position of the domain wall. So on one side, they have to be declared infinite. So they simply disappear from the spectrum. And on the other side, they relax to 0. So this is a domain wall that breaks original symmetry by Q and Q minus 1 units. So the classical fields have this block shape of the size Q minus 1 times Q. Well, this is the starting point of describing this domain wall. So at leading order in perturbation theory, this is just the classical solution. The ADS dual that describes this set strong coupling is also known. It is a D-brane configuration, which, well, in ADS, this is a codimension 1 D-brane. So it intersects the boundary at one point. Well, I mean, pictorially it's 1 point, but in fact it's a domain wall, so it's 1 plus 1 dimensional. And then it extends in the bulk and becomes an ADS3 embedded in ADS4 at an angle alpha that in fact is related to this parameter Q that well, it's just the number of units by which the gauge symmetry is broken. So on IDS, the D-brane wraps a two-dimensional cycle, and so well, in CP3 has natural non-contractible cycles, so that there is a two-dimensional sphere that is topologically non-trivial. So one can wrap a D-brane along the sphere, and then it is also pierced by Q units of magnetic flux. So this defines the boundary conditions for the sigma model. They can be shown to be supersymmetric, but they are also integrable. This was, in fact, this is not in the classification list of Deckel and Oz, but George Leonardopoulos showed that this D-brane is also integrable, and so we expect it to be such at weak coupling as well. So at weak coupling, the theory is described by a spin chain, and for ABJM, this spin chain is of the Dvegov-Inarovich type. So the fields are bifundamental, so one has to alternate them. And so the spin chain is naturally alternates sides with representation of SU4 and its complex conjugate. And for alternating spin chains, the natural Hamiltonian is contains interactions of three sides, not just nearest neighbors. And so this, if you do perturbative calculation at the leading order, you find that the dilatation operator is precisely the Hamiltonian of this integrable type. So if you consider one such operator, and it will be described by Bethe ansatz, now this SU4 spin chain. So to compute the one-point function, we just substitute the classical fields for the field operators. And so this way, the one-point function will be expressed as an overlap of some boundary state in the spin chain and the Bethe eigenstate that describes the operator. And so this boundary state turns out to be very, very special in this, that it also preserves integrability. So let me explain, well, how this state looks like and what it means for a state in a spin chain to preserve integrability. So this state will be of the matrix product type. So the fields that we use to construct it, they have three indices. So two of them are color indices and one is flavor. So they have, well, color indices run from 1 to n. But in the classical solutions, the field is restricted to a block of size q minus 1 times q. So these indices will run either from 1 to q minus 1 or from 1 to q. And the flavor index is just a fundamental representation of SU4 or its conjugate. So the fields will then alternate between S and S dagger, and then the color space will form an auxiliary space from the spin chain point of view with the bond dimension that also alternates between q minus 1 and q. So matrix product states of this type are known to be integrable. For instance, in n equals 4, there is a set of integrable boundary states that are of matrix product type. So we may expect that this state will be also integrable. So to show this, it's more convenient to use this representation with the composite fields, where we sort of combine two sides into one. And then bond dimension is either q dimension or q minus 1 dimension. And this representation also makes connection to group theory immediately, because the matrices that describe the state in the auxiliary space are simply representation matrices of SU2. So the simplest case is, so they are characterized by either Q minus 1 dimensional representation of SU2 or by Q dimensional representation. And the simplest case is when this representation is trivial. So the smallest value of Q is 2. And then one representation is, well, defining representation of SU2, and the other representation is one dimensional, meaning that it's trivial. So in that case, the state is even simpler. So there is no trace to take because the representation is one dimensional. And so what we get is a valence bond state, which projects the indices into SU2 singlet. So we take two sides, which are representations of dimension 4 and its conjugate, and we project it onto the subspace where indices can take two values, and also onto a singlet between the nearest neighbor sides. So and then one can show directly that this state is integrable. And well, let me explain into words what it means for a state to be integrable. Now, if you have a boundary in an integrable, well, spin chain or field theory, it doesn't really matter. This boundary will preserve integrability if scattering is elastic and is consistent with the bulk S matrix. So then if we do rotation by 90 degrees, so the boundary becomes space-like, and then time runs along the cylinder. So this property of elastic scattering means that particles, so the state will create particles, right? So it's from nothing. And for integrability to hold, these particles have to come in pairs with opposite momenta. This is the basic property of an integrable state. Basically, the state will be integrable if magnons appear in pairs. The states are parity invariant, and well, with some work, one can show that the state that appears from the D-brane in the ABJM satisfies this property. So it only has non-trivial projections on Bethe eigenstates, which contain all magnons in pairs. So what we want to do now is to compute an overlap of the state with a given Bethe state, and this will give the value of the condensate of the corresponding gauge theory operator. So the Bethe eigenstate will be characterized by a set of 3 types of Bethe roots. So it's the Bethe equations are of standard Lie algebra type for SU4. So the question is how to compute the overlap of a Bethe state with this given state that preserves integrability. So this boundary state is not an eigenstate of the Hamiltonian, but integrability guarantees that it has some nice properties. And in particular, the overlaps of this type of states with Bethe eigenstates were found to have very constrained form, and just by experimenting with many examples, it was shown that they always follow the same pattern. So first of all, there are some selection rules that follow from obvious symmetries. So one symmetry is this reflection Z2, that's a hallmark of integrability, and here this Z2 acts in a bit non-trivial way on the Dynkin diagram, so it not only reflects the rapidities, but it also interchanges the Dynkin labels. So it's in terminology in this field, this state is called achiral. So there is the parity symmetry. It changes the sign of auxiliary roots, and then it interchanges momentum carrying roots and also changes their sign. So the state is also invariant under SU2 cross SU2 subgroup of SU4. So at the level of highest weight, it is equivalent to SU4 symmetry. So only singlets of SU4 will have non-trivial overlaps. So the Bethe states are highest weights. And if you are computing an overlap of a highest weight, then it will be non-trivial only if the number of Bethe roots are equal on all nodes, and this is the condition that the Bethe state is a singlet. And then it's, well, known in many examples that the overlaps of this type of states have a concise determinant representation. So the state is characterized by a reflection matrix. So, well, in the simplest case, it's just reflection phase. So the non-trivial part of this overlap formula is a determinant of the Gadan matrix, but well, in this case, it is not just a determinant; it's a super determinant. And super here refers not to the original supersymmetry of ABJM, but to this fake supersymmetry related to reflection Z2 invariance. So once we have Z2 invariance, we can define super trace and therefore a super determinant. Well, the Gadan matrix is just the Jacobian of Bethe equations. So this factor is basically universal, so it doesn't depend on the model. It is constructed using symmetries. And it's only this prefactor that is model specific, and it does depend on the boundary state and is, well, physically it is constructed from the scattering phases of magnons on the boundary. Now this formula is, well, there is no, well, I guess it should be possible to derive it from TBA, and this was done in some examples by Kaitana and Komatsu. But originally it was derived example by example. So in the Heisenberg model, one can construct boundary states that are integrable. So with a lot of work, one can compute an overlap, and then one finds this formula. And then in some examples it was conjectured, in some it was proven, but it always has this, this form. And so this ABJM boundary state associated with the domain wall is no exception. The formula is again of this type. So the nested equations are, well, here they are a very standard type. So one just needs to compute then the Gadan matrix. Its superdeterminant actually can be factorized, so one can diagonalize the Z2 symmetry. And then superdeterminant is just a ratio of two ordinary determinants, and can be written in, well, in very explicit way. So the overlap formula was actually, well, known. It was derived by Gombar, well, it can be written either through, well, it contains superdeterminant and then product of some Q functions of the spin chain, and they simply come about from the scattering phases of magnons that interact with the defect. So here, in this example, the Q functions, only the Q functions of auxiliary roots appears, and you can see that this Q function, so that there are two Q functions in the denominator under the square root, and one is the outside, and this will have certain significance when we will supersymmetrize this formula. So anyway, this formula was derived, and we can just use it to write down the expression for the one-point function. So the one-point function in the present of the defect has this nice determinant representation, which was generalized by Christensen and Gomber to the case of this generic matrix product state. So in that case, it contains a sum of terms of this type, and this is easy to understand qualitatively. So the state has the form of the matrix product state, so it's like a character in some auxiliary space, which is a representation of space of SU2. So the overlap will also be of character type. So the basic structure of the superdeterminant will be a common factor, and then there will be something, some prefactor under the square root. But the Q functions that stand outside, they instead of a single Q function, we will have a sum of Q functions, and this precise formula was found in this very recent paper by Charlotte and Tomasz. Now to extend this condensate formula to all possible operators, we need to include fermions, derivatives, and well, field strings, so all possible operators that one can imagine. So doing this directly is a very complicated story, because you need to do a computation that goes beyond two loops, so that well, fermions do not appear, and they don't have classical expectation values. Then gauge fields are also not switched on, so one would need to make a very complicated calculation. But symmetries allow one to circumvent this direct computation and just guess the formula from consistency conditions. So we know that to extend the dilatation operator to other sectors, well, one doesn't need to do an extra calculation of diagrams. So it's the Bethe equations are just one just adds a few nodes to the Dynkin diagram to make it supersymmetric, and this will describe all possible operators of the theory. So in this case, the symmetry group is OSP64. So here is the Dynkin diagram. So it has three nodes that describe SU4, and then one add two nodes that make a fermion out of scalars, and then two fermions are equivalent to a derivative, and then one extra node flips the spin, the space-time spin of the field. So since this is the symmetry group is a supergroup, in fact, this diagram is not unique, so that one can write down many Dynkin diagrams that describe OSP4, and there is a symmetry of Bethe equations that allow one to go from one diagram to another, so that this is known as fermionic duality. Basically, one of the QQ equations transforms the diagram to a different grading. So if we start with, if we have fermion node, then we can replace Bethe roots on this node by their duals using the QQ equation. If one re-express the Bethe equations for other roots in terms of this dual fermion roots, then the nodes next to this root, to this original node, will also become fermionic. And so there is a very systematic procedure how to transform the Bethe equations between different gradings. So what is less well known, but it is also true, is that the superdeterminant is the Godin matrix also transforms nicely. I don't know what happens to its determinant, but if one computes superdeterminant, then it basically remains the same up to some factors that are simply Q functions of the spin chain. It's plus or minus 1, right? So the off-diagonal elements of the Cartan matrix are plus 1s or minus 1s. So solid line is minus 1, dashed line is plus 1. Sorry?
In principle, it's all fixed by the Dicke diagram.
Yes, yes, of course. This how this dashed lines and solid lines alternate, it is prescribed from the beginning. So it follows a very systematic pattern. But I prefer to draw different lines for plus and minus 1. Just an notation. Yes. So anyway, then, and the superdeterminant is the most complicated part of the formula. So, so this means that if we know how to write the formula, the overlap in one representation of the Dynkin diagram, we can go to other possible representations by simply doing this transformation that would produce some Jacobian. But since this, well, the formula we expect it to be of the same form for all gradings, it should produce, so this Jacobian shouldn't spoil the form of the overlap. So it should always remain of this type. So there is a product of Q functions under the square root. And the Jacobian should cancel some of these Q functions, produce new ones, but it shouldn't spoil the form of this formula. And this turns out to be a very, very strong condition, so that allows to extend the overlap from SU4 to the whole diagram without doing any calculations. So if we write it in this notation, so these labels now are simply the arguments of the Q functions in the, or how many? So in the, it's arguments of the Q functions in the overlap formula. Then fermionic duality simply, well, first of all, the formula will transform nicely if there is a fermionic Q function evaluated at 0. So if it's in the numerator, then after the duality transformation, it will appear in denominator, and then there will be Q functions on the neighboring nodes that will appear from arise from the Jacobian. And the same holds for the inverse transformation, where the Q function at 0 appears in the denominator. So these are the basic rules that we are allowed to follow. And the structure is so rigid that it is enough to know how what the Q functions are in this corner of the diagram. So the rest is fixed by the consistency conditions. So it is only possible to go between these three diagrams if the Q functions that appear in these two additional nodes follow this particular pattern. And so we can write overlaps for all possible operators and also in all possible gradings. In particular, we can write it in the distinguished grading where the fermionic and bosonic nodes alternate. This is the form of the Dynkin diagram that can be extended to high loops. Like there is a Gromov-Yerry equations which describe the overlap for, that describe asymptotic Bethe equations. So what we expect is that this formula is basically the same at higher loops. If we, instead of Q functions, write replace them, but basically replace U variables by x plus and x minus. Okay, so I come to my conclusions. You can just read them. Thank you for attention.
Thank you very much. Questions?
Can you extend this construction for all loop, not just tree level?
More or less. I think that this formula should, properly understood, should be the extension to all loops. But well, one needs to be careful of how to replace Q functions by, this one loop Q functions with the exact Q functions. This is in principle ambiguous, and the explicit formula has not been written, but I think it's a matter of doing some extra checks to.
Okay. One more question.
Thanks for the very nice talk. So, if I understand you've got the one-point functions of any operator with this boundary state.
Yes.
Written down, and so in principle, you could sum over all these states, all these one-point states, right?
Oh, well, why would they want to do it?
So one thing that would be nice to calculate, I don't know if it's at all possible, would be to calculate the cylinder diagram. So an exchange between two such boundary states. And that exchange is literally just a whole bunch of one-point functions, right? It's just, it goes to some...
So you want to insert two domain walls?
Yeah, exactly. And we know, or at least we know in say, flat space or other simple backgrounds that that whole cylinder diagram is really just, a bulk state propagating.
Yes. So in this case, well, this domain walls, they are all BPS, so they shouldn't interact. So in principle, the string diagram between two D-branes should cancel. How to think about it in field theory, I'm not sure, but I have to think about it.
It's
but
true.
It's a very
it would
question.
Cancel, yes, but you might want to separate it out into let's say the graviton type contributions and the Ramon type contributions.
Yes.
I guess what I'm getting at is there are some nice theta functions that appear usually, and I'm wondering if you are inventing in this way generalizations of theta functions.
I haven't thought about that, but definitely it's an interesting question to see how the D-branes interact.
Okay, one more question from here.
Does this formula have some this strong coupling-like limit, which reminds something from group theory, like Clebsch-Gordan coefficient, or?
A strong coupling.
Yeah, as in the old days we compared this fake strong coupling expansion from perturbation theory with real strong coupling expansion from.
So here it can only be done at the level of basic B-man string. So it can be done, but for some reasons it has only been done for the string that's point-like and which is the ground state of the spin chain. So for which the formula is basically trivial. So, well, I mean, it's trivial up to prefactor. So this prefactor can be reproduced. For spinning strings, explicit string calculation is not very simple. It's not very simple to construct this solution of the string that starts at the boundary, expands, and then ends on the D-brane.
So there is nothing to compare with if you do this fake strong coupling expansion. You remember that one can.
Yes, there is nothing to compare with, just because the technicalities have not been overcome. So no one constructed this solution, but they do exist, and in principle, it's a meaningful calculation that potentially one can do, but no one has done.
Thanks.
Okay, are there any more questions? Okay, if not, let's thank the speaker once more. And I think we can reconvene as originally planned at 10:15. Yeah.